a few words before we get started. So we're here to prepare for the ACS. It's 70 multiple choice questions. It's so you guys are no written response, no free response. You guys are going to need to bring a pink Scantron. A lot of students have told me that they've seen a lot of Orgo 1 and NMR, IR, and mass spec for the ACS. So if you haven't already, I strongly encourage you guys to review this material and go to the Orgo 1 review sessions if you can. So that's that. As we will work through the material here, please feel free to ask questions. You can raise your hands, interrupt me, it's fine. There's no dumb questions. And if one of you guys have a question, usually 90% of the rest has the same questions, but they're a bit shy to ask. So I'll definitely leave some free time at the end for questions. And if you guys have a specific problems you want to work on, we might even finish early. So please hang around and we'll take care of that. If you guys need to leave, it's okay. Just leave quietly to not disrupt the rest of us. Sometimes I get a little nervous with public speaking, so if I mumble or if I make mistakes, please call me on that so that we can rectify it. And without further ado, let's get started. So we're going to get started with everyone's favorite topic, IR, NMR, and mass spec. So we're going to work through the chapter 15. So I have a problem for you, and I'm not going to give you the answer. I'm going to give you like 2 minutes to work on it real quick. So there we go. Had to have my pencil. All right. So we have this compound here. It's a pentane. It has a methyl and a chlorine. I'm going to add a base. Let's say Naomi, right? Sodium methoxide. Then I'm going to add borane and work it up with a base. Okay? So take a sheet of paper and write the intermediates that we're getting. All right, so I'm going to give you 2 minutes to work on this. We're going to have intermediate A, B, C, D, E, F, and G. Yeah.
Is there a worksheet or anything to bring up?
No, it's all here.
Those protons are in the same environment, right? So these.
Thank you. Thank you. So, how are we doing, guys? Still working? By a show of hands, how many are still working? Okay, 1 more minute? 2 more minutes? Okay. All right. Okay. So for those of you who are done, I'm going to ask you the first question. 1. How would you use infrared spectroscopy to differentiate between F and G? D and E. Then 2. B versus F. Should I use IR or mass spec? All right, so let's work through this together. So first we're going to have a base here, right? So what is this going to do? Yeah, exactly. We're going to have an E2. Yeah? Then BH3-THF followed by basic workup. What is this going to do? Yeah, it's going to add water, Markovnikov or anti-Markovnikov? Cool. Awesome. Then, what am I doing here? Yes. I'm basically transforming this into a good leaving group, right? Cool, cool. Awesome. Then with terbutoxide, yes. Yes. Right, so we're going to have one here. What's that? I might, let's see. We are gonna have a double bond here, right? Ooh, thank you guys. Let me see, 1 sec. Da-da-da. Like here, 1, 2, 3, 4, 5. Yes, I did. I did. Thank you. Cool, cool. 1, 2, 3, 4, 5. Yep. Okay, cool. So then we're going to have our alkene on the terminal side. Okay, awesome. Then what does MPBA do? Oh, right. What's that, guys?
Your parent chain has 6.
1, 2, 3, 4, 5, 6. Oh, okay. Awesome. Thank you, guys. All right. So MCBBA forms this into an epoxides, right? And then we have our ethyl. Okay. Now we have a ring opening here, right? So is it going to open the ring on this side or that side? So here we have a carbon, that's a primary, right? Because it's only connected to one other carbon. And this one's a secondary, right? Because it's connected to 2 other carbons. So in ring opening reaction, when we have primary versus secondary, the Grignard is going to favor the primary. Yes?
The Grignard, does it make, I forget, is it secondary or tertiary alcohol?
It depends. In this case, it depends what you have. In this case, you're going to have a secondary alcohol.
So ring openings favor the less secondary?
When you have a ring opening reaction in an epoxides, if one carbon is primary and the other is secondary, by sterics, the primary carbon is going to be the one that's going to be of interest. But if you had a primary versus a secondary versus a tertiary, or a primary versus a tertiary, which one would you take?
Secondary versus tertiary?
Yes. Let's say, no, I meant tertiary versus primary. So this is a case where sterics does not come into play. It's the electronic effects. So let's see. So we have an epoxide here, and we have 2 R groups, right? So that's our tertiary carbon, and that's our primary carbon, right? So what happens here is that this bond is actually a partial bond, meaning that we have a carbocation here, and the bond is resonating between, it's basically forming and unforming at the same time. So this carbon, since it's tertiary, it's very good at stabilizing the positive character. As a result, our nucleophile is going to attack here. So that's an exception where if you have an epoxide and you have one side that's tertiary and one side that's primary, this is actually the electronic effect that's going to predominate. Yes, because here you have a lot more partial positive character on that tertiary carbon. Now, if you had a secondary versus a primary, the bonds here and here are approximately the same, have approximately the same cationic character, and the carbons do here. So as a result, steric is going to favor your primary carbon for your nucleophile. Okay? Any questions on that, guys? Yeah, it's a bit tricky. Just remember that primary versus tertiary, we're going to attack the tertiary because we have a carbocation with a carbon with a lot more partial positive character, and secondary versus primary is going to be the primary because of sterics. So here, to go back to our problem, which side am I going to attack? Yeah, the primary. Awesome. So our methyl here is going to attack, and that's how I get a secondary alcohol with water workup, of course. Okay, so let's keep track of the carbons. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. We have a carbon here, OH, and a methyl here. Okay, so then what's happening here with NaH and methyl iodide? What's that? Is the hydrogen acidic? Good question. So when you have sodium, sodium is usually your counter ion, so it's going to be the one with the positive charge, and your hydrogen here in that case is going to have your negative charge. So it's a hydride source. It's a very potent base. When you use that in a beaker, you'll usually have H2 gas bubbling out. So in that case, what's that? Oh, gotcha. Yeah. Cool, cool. All right. So, in that case, we're going to deprotonate our alkoxide ion, our hydroxide group, and install a methyl. So, all right. Is that what you guys got?
Can you go back from E to F? From like E to F to G again, please?
E to F? Okay, so that's the ring opening? Okay. How to draw F? Okay, so. What's that? Oh yes, the methyl, I forgot to add it. Good catch. Okay, so, all right, so 1, 2, 3, 4, 5, okay. So, this is what we had. We had, let's go back, guys. Okay, 1, 2, 3, 4, 5. Did we start from this? Okay, cool. Okay. Did you guys all get that? Yes? Okay, cool. All right, so then we have our epoxide here with MCPVA. Okay, then we have a green yard, which is, you can draw it this way. So it's going to attack this carbon. Then your ring is going to open, right? Because you're breaking the octet. So I added the methyl here, right? Cool. Then I had my 3, 4, my O here, and my methyl here, right? Okay, so then I just work it up with water, right? Because this has a negative charge. Okay. Okay. Is that what you guys got? Yeah? What's that? Cool. Awesome. All right. Now, just a quick question, just to get you guys thinking. What if I had a chirality center and I was opening a ring? Let's say I have cyclohexane. Let's say I have an epoxide here and a group here, right? So we would have inversion of the chirality center, just so you guys know. So let's say it's cis, it's on top of the plane. If I open this up, right, with a green yard, let's say a methyl again. Let's see, I have 1, 2, 3. I have secondary versus secondary, so it really doesn't matter. And just so you know, I'd have inversion of the chirality center on the carbon that I'm attacking, because this is going to proceed via an SN2. It's just something to keep in mind. Yeah, it's a backside attack. So you'd have an inversion. So that's that. Okay. So then how would I use IR to differentiate between F and G? Well, that's kind of simple, because here we have an alcohol and here we don't. We have an ether. So we're going to have that broad peak 32 to 3600 inverse centimeters, right? Due to hydrogen bonding of the alcohol. Cool. Now what about D and E? So this is D, just did not clearly label it. And E is here. Okay, So what am I going to look for between those two? Yeah, perfect. I'm going to have a bond here between an sp2 carbon and a hydrogen. That's going to appear at about 3,100 inverse centimeters. And also for this one, I'm going to have a C double bond C at about 1650. Now, B versus F, should I use IR or mass spec? Exactly. We have 2 alcohol that's going to show up in our IR. So what we need to remember here is that the carbon chains differ. So we're going to actually need the mass of each compound to be able to differentiate. Yep, so this is mass spec because we have different molecular weights. Now, A versus D. Could we use mass spec? Let's see. So this is A here, and D is here. So what's the difference between A and D, guys? Yeah, the double bond. Here I have an internal alkene, and here I have a terminal alkene. What about the carbon chains? The mass. Do I have the same number of carbons? Yeah, I haven't added any carbon yet, right? The methyl comes after with the ring opening. So they have the same mass. So they're basically isomers, constitutional isomers. So mass spec here wouldn't help because they have the same mass. IR is going to be tough because here we have a hydrogen, and so those 2 bonds are both going to show up. So A versus D is going to be really tough and not feasible. So that's something we're going to leave for the experts. All right, so that's that for this problem. Do we have any questions before we move on? All right, so I have this for you. We have a compound, C4H8, and I'm going to have you draw 5 constitutional isomers. So just a quick reminder, how do I calculate the HDI? Do you guys remember the HDI? It's the hydrogen deficiency index, right? So it's a few simple rules. Basically, if you have a saturated alkane, your molecule is going to look like CnH2n plus 2, right? Okay, awesome. Now, if I have a halogen, right, I'm going to consider it as a hydrogen, right? If I have an oxygen, what am I doing? I just ignore it. Ignore, right? All right, what about a nitrogen? Yeah, I subtract 1 hydrogen. All right, so those are the 3 rules. As far as accounting for the hydrogens. Now, if I have an HDI of 1, that indicates the presence of either a carbon-carbon double bond or a ring, right? CC or a ring. If I have an HDI of 2, then I could have a ring and a double bond. I could have 2 rings or 2 double bonds, or I could have 1 triple bonds, right? Or one of each. Okay? So, what's my HDI here? So if I do C4, I would need to have H4 times 2 plus 2, right? So what would that be? Right? But I actually have C4H8. So I'm missing 2 hydrogens, right? And 2 hydrogens missing makes up for 1 in the hydrogen deficiency index. Okay? No? Back up? Okay. All right. What's that? Yes. This is our formula when the HDI is equal to 0. Is 0 here. For every 2 hydrogens that I'm missing, it's 1 HDI, right? So if I had 4 hydrogen missing, then I would have an HDI of 2, right?
But like, so the N, so our formula is C4H8, our N is 8 that we plug into the equation.
I plug in 4, N equals 4. Okay? Question? Yes. For every 2 hydrogens that I'm missing, you get 1 deficiency. Exactly. Exactly. 1 ring or 1 double bond. Yeah. Hydrogen deficiency index.
And if we can't remember this, we can just draw.
Sure, you could try. You could attempt it. Yeah, definitely. Yeah, well, let's see. If I quickly draw C4H8, so I'll just draw a butane, right? I can do like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10. I have C4H10. Okay. Well, I have 2 hydrogens that, you know, are surplus. So what do? Double bond, right? 1, 2, 3, 4, 5, 6, 7, 8. That fulfills the formula. What about cyclobutane? 1, 2, 3, 4, 5, 6, 7, 8, right? Awesome. And yeah, so that's because I joined the ends here. So when you join the ends of of butane, you have 3 hydrogens here, right? H, 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 H. We know that carbon can only make 4 bonds, right? So if I want to make a bond between this carbon and this carbon here, right? Now I'm breaking the octet rule, so I need to get rid of 2 hydrogens, right? All right, cool. Sorry about my drawing, it looks terrible. All right, so this is how we calculate the HDI. So the 5 constitutional isomers real quick. So I already drew 2 for you guys. right? Cyclobutane and 2-butene. 1, 2, 3, 4. Yeah, 2-butene or but-2-ene, right? Okay, then I'm going to just move one bond at a time, right? So I have another here. And I'm going to move my double bond here. So that's 4. And then we could have an oxyrane ring with a methyl, right? So those are my 5 constitutional isomers. Now, out of those 5s, which one do you expect would exhibit a strong signal at M-15 in the NMR spectrum? So just so we know, M-15, it indicates the loss of a methyl group, right? So I'm basically looking for a fragment that will be quite stable at M-15. Now we remember the rules for stability in NMR. You're looking for a fragment in which your cation is going to be more substituted or exhibits resonance, right? What's that? That's a very good suggestion because it would be a secondary carbocation. However, there is a better answer, a better solution, and that's going to involve resonance. And it's going to be this one here. It's going to fragment like this. So this one here is going to give you this, which exhibits stability like that, okay? And that's going to be your most stable fragment. So this is really the one that's going to exhibit a strong signal at M-15. Yes, because of this resonance structure. Yeah, fragmentation will favor your most stable fragments, right? So this is the compound of interest, which is just butene or 1-butene. Any questions about that one before we move on? This one? This one? Well, let's see. If I fragment this, like here, I will have a vinylic carbocation. And this is very high in energy. Because your pi bond is a region of high electron density. So if you create positive character on that one, it's going to be highly unstable. So no. Any other question? All right, let's go then. So we have this guy, H9Br. Draw me 4 isomers. Yes. So usually I just start by calculating the hydrogen deficiency index, right? So we know that a bromine is counted as a hydrogen. C4H9 plus 1, it's C4H10, N equals 4. My hydrogen deficiency index is 0, right? Cool. So if I don't have any hydrogen deficiency index, I don't have any double bond, any cyclic structure, or any triple bond. So I'm just going to draw butane and arbitrarily put my bromine here. Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9. That works. That's one of the structure. Now let's move bonds one at a time. Let's put the bromine here in the terminal position. So that's another isomer. Now I can't really move my bromine anywhere else, otherwise I'm going to go back and get the same compound. Can everyone see that? Cool. So then I'm just going to move a methyl, right? So let's move a methyl here. So let's create some branching. That's what I meant. So here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. We still have that. What's the last isomer that I could do? Could just move the bromine here, right? Cool. Yeah? All right, so those are the 4 isomers. Now, when treated with sodium hydride, 3 compounds are formed. When treated with sodium hydride, one structure gives you 3 compounds. So, I was going to have you work on this, but we're a bit short on time, so I'm gonna run through it. So, when treated with sodium hydride, this one can give you this compound, and or this compound, okay? This one being a minor and this one being a minor, right? This one's the most stable. So, this is compound A, this is compound B, C, and D, okay? When compound D is treated with NBS and light, and then tert butoxide, right? What do I get, guys? I get an allylic Br, and then an elimination, right? Okay. So this compound here is 1,3-butadiene, right? 1,3-butadiene. And it can be used to synthesize rubber. It's a polymer. And I just want to show you real quick how 1,3-butadiene can polymerize. So remember, this single bond can rotate, right? You'll have some energy barrier in order to rotate it, to convert it from an S trans configuration to an S cis configuration, right? But when that is done, we will polymerize this. So using fishhook's arrow, right? And can you guys see how this can go on and on and on and on, right? So then I would get a structure that looks like this. Right? And so our monomer here is going to be this lot to the N. So that's going to be H2C, CH2, bracket, bracket, to the N, right? Because it can go on and on and on, depending on how long you want your chain to be. So this is just to give you a brief review of radicals. All right. Do you guys have questions before we move on? Okay, cool, cool. All right. So, I was planning on having a break, but we might not have time. So if you guys need a break, you're more than welcome to take it, you know. We'll just go through it and you can catch up later with someone else. All right, so I have a problem for you. When 4-methyl 1,2-cyclohexane diol is treated with concentrated sulfuric acid. So first step, write down 4-methyl 1,2-cyclohexane diol. So first off, I'm gonna draw my cyclohexane. I know I have a 1,2 diol, so 1,2, right? OH, and then I want 4-methyl. So remember to put my methyl. I'm going to go 1, 2, 3, 4, right? Oh, sorry guys. Thanks for letting me know. I'm going to go 1, 2, 3, 4, not 1, 2, 3, 4, right? Because, I mean, in any ways, you come to this position, but we want the lowest number, right? So just to keep track of our carbon. Okay? All right. When this is treated with concentrated sulfuric acids, the product has a molecular formula of C7H12O. So concentrated sulfuric acid. Then we have a compound with C7H12O. Okay. We know that the IR spectrum gives a strong signal at 1720 inverse centimeters. Identify the structure and show the mechanism for its formation. So first thing, again, I'll be calculating the hydrogen deficiency index. So remember, when we have oxygen, what do? Yeah, we ignore it. If we have a halogen, we count it as a hydrogen. If we have a nitrogen, we subtract a nitrogen. Awesome, awesome, awesome. And for 2 hydrogens that I'm missing, it's 1 in the hydrogen deficiency index. So if I'm missing 2, my hydrogen deficiency index is 1. If I'm missing 4, my hydrogen deficiency is 2, and so on and so forth. Okay, so I have a strong signal here. Well, to me, this is obviously indicating of a carbonyl group. So C7H12. So I know that if it was a simple alkane with no double bond, no rings, I would have C7H14 plus 2 H16, right? C7H16. However, I have 12. So I'm missing 4 hydrogens. So what is my HDI? Yeah, it's 2. Cool, cool. So you guys got that. HDI of 2. So I have either a ring and a double bond, 2 double bonds, 2 rings, or 1 triple bond. However, this is the IR spectrum is highly suggestive of a double bond here, and I have a ring here, so somehow I feel that my hydrogen deficiency index are going to be accounted for. All right, cool. So I'll run you through the mechanism. So we all know that sulfuric acid is a proton source. So I'm just going to show you hydronium, right? Because sulfuric acid's in water, interacts with water, and we have free-floating hydronium in the solution. So here we go. I protonate this. All right, so this is a great leaving group. So this is just going to leave. And we're going to have this lot. Right? So when I have a carbocation that can arrange, it will rearrange, right? So I'm not going to have a methyl shift here because it's a carbon away, so it's too far. I'm going to have a hydride shift. So and here it's interesting to see that we have a resonance structure, right? With the oxygen. So then we would have a carbonyl, right? All right, and then I'm just going to use the water that was deprotonated to take my hydrogen off. And this is the resulting compound, which is 4-methyl cyclopentanone, right? 4-methyl cyclopentanone, right? Oh yes, cyclohexanone. You guys got the idea. Because it's a hexane ring. Yes, thank you. All right, so that's that. All right, so yeah. Oh, I see what you're saying. That's a good question. No, actually, both products could form. Sterics? You mean the para? Yes, that would be a good point to consider if I had a tert-butyl group. For the methyl, it's not as a big deal, but that's a great observation. Thank you for bringing that up. Yes, absolutely. Absolutely. All right, any other questions? No? Okay. Cool. All right, so let's move on. Okay, and okay, so I'm gonna have you predict the relative heights of the peaks at m plus 2, and m plus 4 for CH2, ClBr, and CH2, Br2. Better? Okay, cool. So for those two compounds, you guys are going to predict the relative heights of the peaks. So when I say relatives, I mean relative to one another, right? Is this peak 1/4, 1/2, 1/3 of the other one, right? So the relative heights of the peaks at m, m plus 2, and m plus 4 for those compounds. And I'll give you guys 5 minutes. And if you have any questions, just let me know. You guys can also interact and ask your peers. All right, so we're still a bit short on time, so I'm going to jump into this. So let's start with this compound right there, with the 2 bromines, right? So I know that I have about 50% of 81 bromine and 50% of 79 bromine. So that means that if I had only 1 bromine, our peaks at m and m plus 2 would be the same height because I have 50% of each, right? However, I have 2, so I'm going to have m plus 2, and m plus 4. So I'm going to have half of this in that peak and half of this in the m plus 4 peak. And that's as simple as that. So I added this one here, and then here I just have 1/4. So then we would have, this is 1/2 of our original peak. Let's see, this is 1, and this is 1/4. Okay?
Aren't we supposed to know that there's this many bromides with 79 and 80?
Yeah, I would remember it. It was covered in the chapter, in the NMR chapter. Bromine has 50% isotope, I'm sorry. 50% of its isotope has 2 extra neutrons, making it bromine 81 instead of 79. And you've also covered chlorine. Chlorine has 75% isotopes 35 and 25% of its isotope 37. So I'll write it down for you. Yeah, this is a good thing to keep in mind. If you have an NMR spectrum and you see 2 peaks that are at M and M+2 are the same heights, then you most likely have a bromine. If you have a peak at M and M+2 and one of them is the third of the height, the M+2 is the third of the M height, then you most likely have a chlorine. I'll write it down for you. So in bromine, we have 50% isotope is going to be bromine 79, so 79 bromine, and 50% is going to be 81 bromine, giving you those M+2 peaks that are characteristics on an NMR spectrum. Good question. And for chlorine, we have 75% isotopes being at 35, right? And 25% at 37. Okay? So that's a good thing to keep in mind. And that was at the beginning of the semester, so I can understand that it slipped your mind, but and plus we had a hurricane season and classes were canceled. But that's why I'm bringing it up here, so that you can be prepared. So let's do the other compound, CH2ClBr. So I'm going to have a certain height at M, right? And I know that at M+2, due to the bromine effect, I'm going to have half of it here. So this is if I had only one bromine, right? So and no chlorine. So this is the bromine effect. Then I would have 2 peaks equals to each other at M and M+2, equals in height. Okay? Now, I have a chlorine here. So what is my chlorine going to do? It's going to shift my peak by 1/4 because I have a fourth relationship here. So if I divide this peak in 4, 1, 2, 3, 4 segments, I'm going to have 1/4 move here. And then I'm going to have 1/4 moving at M+4. And that's the chlorine effect. It shifts by 1/4. Okay. So then, if this one is 1, this is going to be 3/4, right? Because I lost 1/4. Here I lost 1/4, but I gained 1/4, so this is 1, right? Lost 1/4, so it's 3/4, and here I gained 1/4, so it's 1/4. A fourth. A fourth, because you have a quarter that's going to be heavier, right? So it's going to shift it by a fourth.
I thought that chlorine was a third of the height of the base.
It's a fourth. Is it a third on your?
In my notes, it says a third, and then yours is almost the same size as the base.
Right. Well, no. When you shift it, it's going to be 1/4. And this problems is actually it's been from. I mean, I took it and I kind of tweaked it from your book. So you can verify the work on the solutions manual, which is going to be analogous to what I did. And in the solution manuals, it clearly states that the chlorine effects will shift your peak by 1/4. So just for reference, let me tell you which problem I picked. It's was one of the challenge or the integrated problems. Come at the end of class and I'll show you. I mean, at the end of the session. All right. So, all right. Now, on to this one here. Okay. Okay. Just a quick question for you. Which is more basic, guys, between pyrrole and pyridine? Pyridine? Why? Yeah, exactly. And pyrrole's lone pair participating in aromaticity? Okay, perfect. So we're on the same page for that. Okay, cool. All right. Is this compound here aromatic?
brought some extra batteries, just in case. As you can see right here, they're like half battery.
Yeah.
These mics have a cool little battery indicator on them.
Okay.
So these will probably be fine for Danya's session, but after hers, you might want to swap out the batteries.
Where are the extras? Okay.
Small batteries. Put the old ones to the side, and if anyone from outside comes by, just because these are theirs, just give them back to them. Because they have rechargeable ones, we have disposable.
Is that? Can I see the battery on there?
Yes, it's
Okay.
also right there.
Okay, cool.
So, around that?
So if I see it's about to die, then.
Yes. Hello, 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 hello. These are the headphones for that. Hello. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I was actually presenting, I'd probably enunciate a little bit more.
Right, because like I'm hearing you talking, but I'm also hearing static.
Hello?
And
The static should.
something over here is, because I can hear my.
I think it's because I'm too close to the receiver. Is it better? Less static? Hello, 1, 2, 3, 4, 5. Oh, wait, I actually remember that. That was going on with the stream last time. I think it's just something wonky with the microphone.
Okay.
The person's voice is audible enough.
Okay.
We had to deal with it last time. Take those off. Just because these might have a weird thing that when you turn them off, they feedback static.
otherwise I can.
Yeah, I got you. When does it start recording? 25 or something?
I can start recording in 5 minutes, and then I'll start the stream in 10.
I was making sure so I don't say anything on there. Okay, is it working? Is this better? Can you hear me? I'm not allowed talking. It's very low? Is that just because I'm talking softly? Is this better? Better? Okay, sweet. Thank you.
I'm just giving you a heads up so that you don't say something that you don't want recorded.
Yeah, okay. Sounds good.
So what I'm doing today is I'm picking up where I left off yesterday. But don't worry about it because I am posting an answer key. So the answer key will have the answers to all the questions. So if you missed whatever yesterday, that's fine. The people who came yesterday and they're not here today, they'll get everything as well. But it's just, I think it's better instead of like redoing the whole thing from the beginning and not getting to like the end, just doing like the second half today. Okay? Oh, that's a good question. So if you go to ucfstudyunion.wordpress.com, you go to chemistry, and then you go to Organic Chemistry 1 with Karina A, and my review is going to be there. And that's probably where I'm going to post the answer key too, so just keep an eye on it. I'll probably post it like a few hours after the review today. Any questions? Okay, cool. Also, I'm really sick, so please don't make me scream. If you guys have a question, just raise your hand, but I don't want to have to talk over people because my throat really hurts, like bad. So please be nice, guys. 52. Yep. I know it jumped. I don't know why. Were you able to find it?
I'm trying to. I think I'm on
Are you in
schedule.
chemistry? Okay, yeah,
Yeah,
so keep going
chemistry.
down. And it's going to be all the way, okay, Joshua, Natalie, Karina, that's the one.
Okay, and this, okay.
Yep, that's the one. Yep, and we're on question, I'm going to start on question 55 today. If I finish the review and I still have time left over, we can go back to the beginning for the people that were in here yesterday. I don't mind doing that. But today we'll start at 55, okay? Oh, it's good? Okay, cool. Huh? Oh, thanks. Okay. No, I'm studying. I have my biochem final on Tuesday. Yeah. Huh? Oh, yeah. It's 10:30. Okay. Oh. Yeah. Yeah. 10:30. All right, guys, so it's 10:30, so we're going to go get started. So again, you guys can find the review on this website, ucfstudyunion.wordpress.com. I'm going to be posting the answer key here too. So just go to this website, answer key will be there. Whatever you missed, it's okay. If you look through the review and you have a specific question about material that I already covered, that's okay, just raise your hand and let me know. But like I said, I'm going to start at 55, okay? All right. So, all right. Cool. Can everybody see the screen? Okay, perfect. So which of the following is an energy diagram for a three-step reaction? B? Okay, why? It has 3 transition steps. What are the transition steps? The minimums? You sure? Maximums? Yeah. Okay, so which one is it, guys? All right. So that's 1 step, 2 steps, 3 steps. Cool? Okay, and how many intermediates do we have in this reaction? 2. Awesome. So this is I1 and I2. Awesome. All right, what is a transition state? D? Okay, what do you guys think? C? So we just talked about it, right? So what do we say the maximums were? Transition steps. Yep, exactly. So it's going to be C as in cat. All right? Questions?
Letter D would be intermediate.
I think so. Not one, because it has to like say the minimum, but I think so, yeah. That's okay. All right. Oh, there we go. What is an intermediate? C? Are you sure? Okay, so C. So let's go through all the, what did you say? Okay, so let's look at all of them. So a point on the reaction pathway that has a discrete lifetime. Is that true? It could be A? Can it? It actually exists a little bit, right? With an intermediate, that's why in SN1 and E1 we can even have rearrangement because we actually form a carbocation. It's not like in an SN2 and an E2 where it's all happening at the same time. So like the intermediate is not actually forming because as you're doing the attack, something is leaving. So which one do you guys think, guys? A? All right.
It doesn't necessarily have to be halfway. That's my thought.
Good point. All right. So 58. Identify the nucleophilic atoms in the following molecule. A? E? Awesome. So electron-rich atoms. Hey, that's a nucleophile. What's an electrophile? Electron deficient. Is everybody good with those two definitions? Anybody need to go over it? No? Okay. So we're looking for the nucleophilic atoms. So which ones are they, guys? Oxygen and nitrogen? It could be. Yeah. So that's both B and C. So E as an elephant. Everybody good? All right. So which of the following cannot be an electrophile? A? Did you say A? Yeah. Okay, why?
Because the positive sign is on the carbon, so it's a carbon atom, you wouldn't be able to.
But what is the definition of an electrophile?
Oh, never mind. I thought it was the.
Okay. Electron deficient, so anything that can have a positive charge, right? So can that be an electrophile? Can it take electrons? Yeah? Okay. What about B? Are you sure? Okay, so bromine could be a nucleophile, but what about the carbon that's bonded to that bromine? Could that act as an electrophile? All right. What about in C? Oxygen could be a nucleophile, right? But what about the carbon? Could it be an electrophile? Why?
Because the oxygen is withdrawing.
Exactly. So you even have a resonance structure, right? So this can go up here, which gives a positive charge to the carbon, right? Okay. So it could act as an electrophile. Can a negative Br act as an electrophile? Why not? Because it has a negative charge. What do we say an electrophile is? Electron deficient. Awesome. Everybody good with this one? Yeah? Okay. So 60. For the following reaction step, indicate which pattern it belongs to. So what do you guys think? So you guys have been doing these mechanisms, right? The whole semester. So this is just kind of like quick review. Nucleophilic attack, why?
Because the double bond is close to electrons are going to oxygen, and that's going to be a carbon ion.
Awesome.
So then the oxygen is going to attack.
The oxygen can attack that carbon. And it's forming a bond, right? So that's the definition of a nucleophilic attack. So, C? Everybody good? All right. So, 61. For the following reaction step, indicate which pattern it belongs to. Rearrangement. Everybody agree? Why? How do you know? Awesome. So Also, what is your other clue other than the fact that you're moving the hydrogen with the electrons?
The charge is more stable.
So you're moving the carbocation, right? So is that, can you have rearrangement when there's no carbocations present? No, right? Okay, cool. So 62. What is wrong with the following mechanism?
The arrow leading the formation of the CDR bond should start at the bromine atom.
Awesome. Why?
Because generally with something like a bromine anion, it's a nucleophilic attack. Therefore, the nucleophile is attacking carbon.
Awesome. So when we're drawing arrows, guys, where do the arrows have to start? They start at the electrons, and then they point to wherever the electrons are going, right? We're showing the flow of electrons. So everybody good with D? Okay, cool. So 63. Identify the sequence of the steps in the following reaction. Proton transfer? You sure? The first one? Okay. And then loss of a leaving group? Are you sure? Is anything leaving? Are we losing a group? So can that be loss of a leaving group? No. So it's not a loss of leaving group, so we know B is out. We said the first one is a proton transfer, so C is out. Okay, so now we have proton transfer or nucleophilic attack for the second step. Do you have, okay. What are you moving?
Oh, another hydrogen. I was looking at the oxygen, so that has to be A.
Right? Proton transfer, 2 proton transfers, right? Everybody good with that one?
Can you explain to me again why is a proton transfer at the second step?
Sure. Okay, so what are our options?
It's either
Like just in general, what are the mechanism errors that we can use? So we have nucleophilic attack, we have loss of a leaving group, proton transfer, and a rearrangement. Arrangement. There we go. Okay. Can it be loss of a leaving group? No. Okay, so we know loss of a leaving group is out. Can it be a rearrangement? Why not? Right, right. That's your first hint. Rearrangement occurs when we're trying to form a more stable carbocation, right? When we're trying to go like from a secondary carbocation to a third carbocation. That's not what's happening here. So that one's out. So now we have between a nucleophilic attack and a proton transfer. So which one do you guys think it is? Which one can you guys take out?
right. It's just because of the hydrogen which is in the corner, right?
Right. I know it's a little weird, but we know for sure it's not a nucleophilic attack.
Yeah.
Okay, cool. That's okay. So proton transfer. Everybody good? All right. So 64. Identify the sequence of steps in the following reaction.
Talk about this one a little more as well. So your pelvic diaphragm or your pelvic floor, I'll write floor here so we can remember, it's the same thing, is made up of the levator ani muscle, which has 3 parts, plus the coccygeus, which is also the ischio-coccygeus, same thing, slash. Okay? So we need to know the 3 parts of levator ani because you might be asked which of the following muscles does not help form the levator ani, right? So we need to know both parts of that. Or he might not write this, but he might write all of its parts. So we don't want to miss a question just for that. So the 3 parts of the levator ani are the puborectalis muscle. And this one is key for fetal continence. So this is the main muscle responsible for that. You also have pubococcygeus, and then you have iliococcygeus. So remember, this is kind of a tricky one. Ilio is part of levator ani. I remember it because of L, so L and L. And ischio is its own thing. So I think that's a pretty easy point to kind of like mix up on your head on the test. Cool. Something else I was going to write. I'm going to continue this down here a little bit. In males, this attaches to the wall of the prostate, okay? So then we call that levator prostate, like this, E at the end. So it attaches to the wall of the prostate. I'm not going to write that out, but y'all know. In females, it attaches to the urethra and the vagina, and that's called pubo.
All right, so, and we said it's a heptane. All right, so what are we going to name this? Awesome. Okay, good job. So we also have chirality. So what is this? What is the configuration of this chiral center? S? Everybody see it? Or does anybody need me to go over it? Chirality. Right, awesome. Yep, good point. So this is 1, 2, 3, and we know we have a hydrogen in the back, right? 4. So this gives us R, but our lowest priority is on a what? It's on a wedge. So what do we have to do? Flip it, right? So this is S. So we have S, 4,5-dimethyl. What else? Oh, thanks. So S, what is it? 2-bromo, 4,5 dimethyl heptane. So that gives us what? B? Right? Cool.
Question, because on the test I did the same thing when they're on the wedged. I did it, normally, and then I will just flip it. And then I got some of them wrong. And he showed me a technique where you just have to write, put the numbers, and then from that you have to flip it or something. Like, it wasn't right if we just flipped it and we did it backwards. So I don't know if there's a special occasion.
You have to make sure. Why do we have to? That's a good question. Why do we have to flip this one? What was on the wedge? The lowest priority. If the lowest priority is not on a wedge or a dash, can we use our rule? No. What do we have to do then? Right, swap the groups. So maybe that's what you're talking about. When the you only have to look at where the lowest priority is. So if your lowest priority is on a dash, what do? So your lowest priority is on a dash. What do you do to the configuration once you figure it out? Do you keep it or flip it? Keep it, okay. If it's on a wedge, what do? And what is the special situation with this? When it's not on a nor on a wedge or a dash, right? So if it's on neither, then you have to switch the groups. Right? Does that make sense? If we have time, maybe we can do a problem like that.
I know how to do it, it's just that I didn't remember that.
Yeah, exactly. Because those, yeah. Everybody good with this, guys? All right. So now 66. How many primary carbons are in the following compound? Two or three. Okay. How did you guys figure out how many there were? A carbon that's only attached to one. So is this a primary carbon? So are any of these in the benzene ring a primary carbon? Okay. Is this a primary? This one? This one? This one? This one? Okay. This one? All right, so that's 2. This one? 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 Yeah? Okay. So what is it, guys? 3, okay. So I know some of these are like, some of the questions that sometimes like you have to do is just a matter of taking the time to go one by one. I know sometimes it's like a little tedious. Yeah, but those are easy points that you can get. You know what I mean? Like the way that I see it, like when I'm taking tests, is that if I know I'm really slow on a problem and I know how to do it, I'll still just skip it because I want to go back when I have time. How long did it take us, even though we went carbon by carbon? Maybe like 20, 30 seconds at the most. And it's pretty like easy points that you can get that you don't have to miss, right? So always try to get what it's like easy, quick, and then you can go back. Even if you know a concept, you can still go back later, right? Especially if you know you're like a little bit slower at doing those problems, right? All right, 67. Which of the following is a reasonable definition of a concerted reaction? C. So it is a reaction in which all bond breaking and bond forming occurs at the same time. Everybody agree? So, okay, cool. So that can be an SN2. What else can this be, guys? E2? Awesome. All right. So which of the following is not a possible step in a substitution reaction? So this is just kind of mechanisms, right? So I heard C. D or B? D? Okay. Why? So who said C? Okay, why C?
Unless we just assume that there's some sort of reagent, you can't just have the bromine leave on its own.
Are you sure?
I mean, it's a good leaving group, but it can't just leave like that.
Always? Are you sure? What about in an SN1? In an SN1, what is the mechanism of an SN1? Bromine leave on its own, and then you have a nucleophilic attack. So you can have a leaving group leave on its own, right? Okay.
Primary carbocation for D, that's why.
Okay, good point. Yeah, well,
Because of an addition reaction.
awesome, right? So in here, if we look at D, this looks like one of the steps in one of our addition reactions. And that's not a substitution, it's addition, right? All right. And this could be part of an SN1. This could be a step of a substitution reaction, right? Because all we're doing is first protonating the OH to, why do we protonate it? Awesome. So this makes it a good leaving group. What about A? What kind of reaction is that? SN2. Awesome. Everybody good with these? Did you have a question? Yeah.
So, if there's like a double bond and something, it's pretty much, it's just addition.
So that's a good question. So when we're substituting, what are we doing? Like, what is the overall idea of the reaction? We're replacing one group with another, substitution, right? What do we do with elimination? You're creating a pi bond. Cool. What do you do with addition? You're breaking a pi bond, and you're adding 2 groups to the alkene. Cool. What other reactions do we have? If I do a double elimination, what will I get? A what? Alkyne. Awesome. I'm sure there's more, but I can't think of any at the top of my head right now. But yeah. So D, that's like you said, that's an addition, right? We have an alkene. We're breaking that alkene, and we're adding 2 groups on the side. That's just part of the mechanism, but it's not the whole mechanism. So just take a look at those mechanisms and remember your reactions. Because sometimes, even if you don't necessarily remember your reagents and you're not sure what the product is going to look like, if you know the mechanisms, you can come up with the product, right? You can always draw the mechanism and just see what the product's going to be. Okay? All right, 69. Which of the following is a product of the following SN2 reaction? What is it? D? B? Okay. C? One of those two? All right. So let's look. So we said that this is an SN2 reaction, so what's going to happen? It's going to happen all at once. What's going to happen all at once? Okay, so a strong nucleophile is going to do a nucleophilic attack, and the bromine is going to do what? It's going to leave. Awesome. It's C? Okay. Awesome. Okay, everybody good with this one? D? We can do it. So let's count the carbons, right? I always say count your carbons. This is how you can avoid silly mistakes. Because sometimes you get the hardest thing done, and then you mess up when you count the carbons, and you put an extra carbon in there, and you still get the answer wrong. And that's a silly mistake to have, right? Yeah. Okay, that's a good point. So let's look at both of them. Okay. All right. So let's attack first. So it's going to attack here. What kind of attack is this? Backsided? Awesome. So what did you say we were going to have? Inversion. Awesome. So it's going to be inversion. Okay. So let's count the carbons. We have 1, 2, 3, 4. So when I form the ring, I have to make sure there's only 4 carbons in like that whole ring, right? So I have my oxygen that acted as a nucleophile, and then I have 4 carbons. So 1, 2, 3, 4. So we know like it's forming this ring. And then we have a methyl group, and that methyl group is on my 4th group. So let's just number 1, 2, 3, 4. So I know I'm going to have a methyl here. Everybody see that? And that's where my 5th carbon is coming in here. All right? Does that make sense? Everybody good? All right. So now let's look. So my Br was on a wedge. Where is my H? On a dash. So when I close this, we said we're going to have inversion, right? So if... So I know with a ring, it's a little harder to see the inversion, because like it does it like in a weird thing, but in this case, the methyl is gonna be on the wedge. Yep. I know it's like kind of weird, like to see with a ring, but if you're not sure or if you're professional, it's because it's like when it closes, it's a ring, and like just because the Br is on a leaving group, the Br is on a wedge. It's kind of hard to explain just because it's a ring. I would just go to your office hours, like with your professors, if they still have office hours, and tell them to explain this one to you. But just remember, with an SN2, what do you have? Inversion. I don't think they're going to give you one like this, though, to be honest. Yeah. So in this case, remember, the methyl is on a line. Right, it's on the plane, so that's why like when you rotate it, and I'm really bad at like rotating groups, so that's why like it's really hard to explain why. But just go to your professor's office hours. They can like go over that, and like if they tell you otherwise, just go by what your professor says. But this one is C. It's not A. And remember, this methyl is not on a wedge or a dash, so that's why it's harder to see. It's on the plane. So when we have inversion, it like pops it to the other side. Okay. Okay, so 70. Rank the following substrates from most to least reactive in an SN2 reaction. So again, what kind of attack do we have with an SN2 reaction? Backsided attack. So what do you need for that? What kind of substrates? Primary? Okay. More reactive than what? Tertiary? What's in here? What's in the middle? Okay, secondary. Oh, also, just before I forget, if you guys have like a little bit of trouble with SN1, SN2, E1, and E2, and looking at the competition, like what's happening, which one favors what, if you guys go to ucfsi.wordpress.com, I have not taken any of my worksheets down. I think this was on exam 2 for Dr. Dowdy. So if you go to like exam 2 material, there's going to be links there for some PDFs that can help you see. Like it just pretty much organizes all the information and tells you SN2 is favored by this, SN1 is favored by this, E1 versus E2. So if you guys just need a refresher, I have that worksheet there, so it's very helpful. I got that worksheet from my SI leader when I took Argo 1, and it really helped me, so I really, really, really recommend. And I have other worksheets on my website as well. So, like I said, I haven't taken anything down, so everything from exam 1 is on there. So that can be a good refresher. All right? So which one is the most reactive here? Methyl. So this is 1. What's my second one? C. Third? B. And fourth? D. Yes. But you won't form the intermediate because it's an SN2. So you won't form the carbocation, right?
It doesn't react at all. It doesn't
Right. Awesome. So what is this one, guys? So this is C. Between what? Between which ones?
I was saying, what's the difference between B and D? Because I thought they were both.
This is an aryl group. So because like this is directly coming off of the benzene ring, that's what's even less reactive. Everybody good with that? All right, cool. So 71. Rank the following substrates from most to least reactive in an SN2 reaction. So what are we looking at here, guys? So right, so we have different leaving groups now. So what is usually the trend for leaving group? Down the periodic table is what? Is it a better leaving group or a worse leaving group? Better leaving group? Everybody good with that? Okay, so now that we know that between CL, I, and BR, which one is the best leaving group? I? Everybody good with that? Oh. What's the second best leaving group? BR? Okay, so now we just have to pick between A and B, right? Because they're both the same leaving group. So which one is a better leaving group? Well, they're both CLs without the double bond. Okay, cool. So 3, 4. So CDBA. So B? Yep. Everybody good? All right. So 72. Rank the following substrates from most to least reactive in an SN1 reaction.
The opposite trend of
Opposite trend of SN2. So what is that? No. Aryl group is still bad.
I thought it was the opposite, like exactly opposite. That was last in the SM2.
Aryl is like just bad for in general.
So then tertiary is favored.
So tertiary is favored over what? Over what? Over what? Over methyl. And do we have anything that's more reactive than tertiary? Allylic, awesome. And what's more reactive than allylic? Vinylic? Are you sure? That's worse, right? Which one is better than allylic? Benzylic, awesome. But it's different though. That's a good question. This is why I brought it up. Before we get into that, why do we notice this trend with an SN1 reaction? Awesome, because in an SN1 we're forming a carbocation. So when you form that carbocation, you want like the most stable carbocation that you can have, right? Okay, cool. So let's talk about benzylic and aryl for like 1 second. I know. It's just like a matter of recognizing positions. Okay, which one is which in this case? Yeah. Benzylic. And this is an arrow. And before we get into this one, let's do allylic and vinylic real quick. And then maybe this one will help you out a little bit more. So, which one is allylic? The top one. And vinylic? Awesome. Which one is more stable? Awesome. Awesome. Because of resonance? Because of resonance. So this is really unstable. Cool. So what will the resonance structure look here? Awesome. You guys are going to do great. Do I have resonance structure here? Right? So you see the difference in positions, right? The allylic position is 1 away from the carbon. Vinylic is right on the carbon that's participating in the double bond. Does that make sense to everybody? All right. So now let's look at benzylic and arylic. Right? Benzylic, once this leaves my carbocation, it's going to look like this. Kidding, this goes away. Can that be stabilized? How? Resonance, right? We can do the same thing. We can resonance, and then this can move, and then this can move. So it's like really, really, really stable, even more stable than allylic, right? But what about this one? Once this leaves, my carbocation is on the double bond. Awesome, so it's kind of stuck there. We can't really do anything to stabilize it. And it's, what kind of hybridization is the carbocation on? sp2? Yeah. Everybody good with this now? That's a good question. So we said for SN1 and E1, what do we form? Carbocations. So if we form a vinylic carbocation, how stable is that? So will it want to do that reaction? We need a stable carbocation, right? The more stable the carbocation, the more likely it's going to do SN1 or E1. That's why we like benzylic, allylic, tertiary, secondary, primary. That's why we see that order. Everybody good with that?
You don't want a carbon that has a positive charge and has a double bond with another carbon.
Not necessarily, because if you have an allylic carbocation, that's stable.
I know, but the plus charge isn't on the...
Right, exactly. Yeah, but like, because what I heard was if you have a double bond and a positive charge, it's going to be unstable. But it just depends on the position that it's at, right? On the carbon, not stable. 1 away, very stable. Everybody good with that? All right. So now we go back to this one. Leaving group is the same, so we don't even have to look at the trend, right? Because they're all I. So we just got to look at what kind of substrate it is. So which one is going to be the most stable? A. Then what? B. Then what? Then what? So that is A. Everybody good with that? All right, cool. 73. Which of the following is the major product for the following SN1 reaction? Oh, yeah, it's there. So who tried the review already before you guys got here? Okay, so one person. Oh, you did too? So? All right, so I'll give you guys like 2 minutes. Try to get the reaction done, and then tell me what you come up with, okay?